Thank you. So this is joint work with Rasmus Ibsen-Jensen from IST Austria and Abraham Neyman from Hebrew University. So here my plan of the talk is to spend quite a lot of time on actually introducing the actual game, the big match, and then present our result, but not try to talk too much about the actual proof. So let's start. In the paper we started with the ancient game of odd and even. So it's a two-player zero-sum game, and player one picks a number of items. It could be knuckle bones and places in her hand or his hand, and player two must guess whether an odd or an even number of items was hidden in the hand. And now it's revealed how many were in the hand, and if the guess is correct, player one loses a point, otherwise player one wins a point. So it's of course very easy to figure out what to do in this game. You just hide, let's say, one or two items with probability 1/2 each, and player two also guesses even or odd with probability 1/2, and it means that the value of this game is 0, and it's actually almost, but not quite, equivalent to the well-known matching pennies game. So if we just look at a small portion of the game matrix, you see the matching pennies game. So what is the difference between this game and matching pennies is that actually you can hide more items, but you can claim that these are just copies of the other actions. But in some settings there might actually be a difference. So you can think about that. So we start from this game, and now we try to build on top of that. So let's consider a repeated version. So now you don't just play this game once, you play it a number of times. This might be a large finite number of times, or it might actually even be infinitely many times. But of course, since each round is just the same game, you just play as before. Each round is played independently as before, and each player ensures 0 points is exchanged on average per round. So now to actually make it interesting, so we now are ready to talk about the big match. So it's a variation of this repeated odd and even game. And actually here we go to the matching pennies case. So player one only has 2 actions. You can hide 1 or 2 items. And now as long as player one hides 2 items, it's just as before. If player two guesses correctly, player one loses a point. Otherwise, player one wins a point. However, now if player one ever decides to hide 1 item in his hand, that's called now the stopping stage of the game. And that means that from now on and ever after, in each round, you don't actually play anymore. You just copy the payoff of the stopping stage. So it's a really dangerous action to play for player one. You can make a matrix representation, and you can imagine generalizing that, and that's called an absorbing game. So it's just like a matrix game, but now we have some elements which have received a star, and that means that if the outcome of the game is in that particular entry, then that's going to be the actual average payoff assigned to the game, or the payoff per round from now on ever after. So in the big match, I'm going to denote the action of hiding 1 item now for the absorbing action. I'll not talk about the actual number of items hidden. So this is, a question.
Is there any motivation for such kind of a formulation? It's kind of a grim trigger or something like that?
Okay, just next slide. So this here is one particular example of a much more general game model of stochastic games. So with this you can model a lot of things. So it's a finite 2-person zero-sum games played on a state space, and here we look at the finite case, we look at the 2-player case, and the zero-sum case. So we have a finite set of states, and now we have finite set of action spaces for each player. And there's a payoff function that depends on the current state and the actions chosen by the players in that state. and you transition from state to state in this game, given by a transition function. It takes a state, a pair of actions, and then it induces a probability distribution on other states. Okay, so this is a very general game model, and you can model all sorts of interesting things in this. So why is the big match in particular interesting? That's for historic reasons. So it's a simple case that turned out to be difficult to analyze. And it was also it really showed a very important thing about stochastic games. Once that was solved, and we'll get to that, things led to actually solving stochastic games in general. So it was an open problem for many years if the big match actually had a value. Okay, so how to play the big match? Let's look at the two players. So player one has an easy task. Just play as in the repeated odd and even game. In that way, you can ensure that player one receives at most 0 points on average per round. Perhaps player two might even be able to do better, but let's see. So player one, there's a relatively easy case. That's if player one actually knows how many stages are going to be played of this game, and the number of stages played is actually a finite number. Then there's a unique optimal strategy for player one, and that is going to be that you play the absorbing action with a probability that start out being very, very small, 1 over the number of stages plus 1, and it gets all the way down to a half at the very last stage. And by that ensures also you can analyze that player 1 ensures that player 2 receives at most 0 points on average. So the value of this game is 0, and another observation is that this is actually the unique optimal strategy for player 1. An easy consequence of that is that if player 1 does not actually know how many stages there are in the game, or maybe the number of stages is actually infinite, there is no optimal strategy for player 1 in this particular game. So now the question now is, can you get an epsilon optimal strategy? And that was an open problem for many years. And maybe one obstacle is that if you think about it, you get worried about the sunk cost principle. So you're playing the game and you don't know how many stages are left, and you somehow have to decide upon the stopping action or the stopping stage. And you can also quite easily see that if you decide in advance for each state, for each subsequent state, you're going to play the absorbing action with a certain probability. That's called a Markov strategy. That's completely worthless. You cannot ensure anything. So you'll get -1 points, maybe plus epsilon for any small epsilon at most. So sunk cost should sort of say that. Yeah, you're looking at the average number of points per round. Yeah. So you're at some particular stage, and why should the past actually matter? Because that has already happened, and you should optimize towards the future. So that should be independent of the past, and then it seems that you should use a Markov strategy, and then it seems you can't do anything for player 1. But that's an incorrect analysis. So it was shown by Blackwell and Ferguson. So that's probably like 11 years after the definition of the introduction of the big match game, that player 1 actually has optimal strategies in this game. And here's one particular strategy. So you're going to keep a statistic on the game, and you're going to maintain a counter. Player 1 is going to sum up the payoffs received in previous stages, and that is going to dictate what is the probability of playing the absorbing action. So one epsilon optimal strategy is to play with probability 1 divided by n plus this current sum of payoffs, everything squared, and n determines what epsilon you can achieve, so make n a really large number. So that requires some work to actually show that that works, and I think it's quite surprising a priori that it actually works out. For the purpose of our work, some things to note about this strategy is that if you think about actually implementing this strategy, you need to have an infinite amount of memory states because you're keeping account on the sum of payoffs, and you are playing maybe infinitely many stages, and your payoff can then tend to infinity. You need to be able to count that or represent that. But it's not something you need to store privately. You can even tell player 2 what is the current memory state because he could compute it himself. Also, it doesn't really depend on the states number, the clock, which is going to play a role in our result. So we are interested in maybe simpler strategies from the point of view of storing memory. So let's define what is a memory-based strategy. So it's something where you maintain a memory state. Let's just encode it as an integer natural number, and you update it after each stage. You get the current time or the time of the clock. You get your current memory state. You also get what the opponent played. Now you you can make a distribution on next memory states. And also you need to be able to decide which action to play in a given stage. So you get as input the time and your current memory state, and now you can output a probability distribution on your actions. This, of course, generalizes completely to stochastic games. You just need to introduce small parameters like knowing what is actually the state of the game you're in and what action you played yourself. We're going to be interested in low memory strategies, so where your memory state is just restricted to be a finite set, let's say of k elements. We say that's a k memory strategy. We can also talk about the update function being deterministic if it is actually not a distribution on next memory states, but actually a function, a proper function. You can also talk about dependence on the clock, whether you actually use the given parameter t, what is the actual stage number. All right, so now I'm actually in a position to state our result. So what we show is that you can make an epsilon optimal strategy for the big match that so it depends on the clock, and it only uses 2 memory states, so 1 bit of memory. So it means that you can ensure on average minus epsilon points in the infinite game and also in arbitrarily or in large enough finite games. All right, so that's our result. Let's compare with some negative results known. So you can't do anything if you are a stationary strategy. That's easy. And I also mentioned that a Markov strategy is worthless. It's also known that if you don't use the clock and you use finite memory, you can't do anything in the big match or even in stochastic games in general. And also a result by myself and Rasmus, Ibsen-Jensen, and Mikhail Kautsky is that you can't get away with using finite memory, but a deterministic update function. All right, so now let me just briefly describe our strategy. So one thing is that we split all the stages into epochs, and the ith epoch is going to be of length about log I up to a constant. And you have to really make the correct constants here. And now you're going to, in round t, so I'll call them rounds inside an epoch, you're going to play the absorbing action with a certain probability. And it's this probability here where you take the sum of all the payoffs received so far in the given epoch and use that to compute a probability. So you might think that how to actually implement this strategy. So I'll get to that. There's a technical thing I'll just put up, but not say. So the crucial insight of our paper is that you can actually implement this strategy that seemingly depends on the history just by storing one bit of memory, but also knowing the clock. And just some more details. So Blackwell and Ferguson, they gave actually several epsilon optimal strategies for the big match. Here's another type of epsilon optimal strategy. So it looks a bit like the one we are doing. There's something like 1 minus epsilon to something where you have a sum of rewards. But the important thing is that here there's a lower bound, so you don't put your count less than 0, so there's a max with 0. And in our case, we have a counter, but we're going to start it at the actual length of the epoch. And that means that we'll never get down to a count of 0. And that's maybe surprising that actually works. And I think maybe I'll not have time to actually describe how it works, but here's an equivalent way to state our strategy. So that's a slide that shows that you can do it with just 2 memory states. So you're going to have an update and an action function. And one memory state is going to say that you're not going to play the absorbing action in the given epoch anymore. And you're going to switch to that with a certain probability in each round if the actual payoff received was 1. Otherwise, you're going to play the absorbing action with some probability. So that's depending on the actual clock and the memory state. And that's it. Let me round off with a few open problems you could consider. So this strategy I just presented, it's very important that the memory is kept private from player 2, so it wouldn't work otherwise. Because player 2 would then know that we're not playing the absorbing action anymore in a given epoch once we have switched to that state, and that can be exploited. So what is the case of public memory? How much memory do you need to store to have epsilon optimal strategies? You can also think about recall, so you remember a certain amount of the history, a number of stages back, and here there might be a difference between the big match and the odd-even game. But the most interesting thing is to generalize everything to the full model of stochastic games. All right, thanks.